This is section 2, algebraic approach to limits, example 6. Now, we want to find the limit as x approaches positive and negative infinity. We did this when we looked at graphs. Now we're going to look at it with rational functions. Now remember, I described when we were looking at graphs, the limit as x approaches infinity and negative infinity as end behavior. And like I said, you've heard of this before. You've heard of this when you were dealing with rational functions. And when you were in Algebra 2, if you took Algebra 2 at Seguin, I told you that to find end behavior, all you do is use the 3 acronyms, BOBO, BOTN, and SDDC. Yes, it is coming back, all right? Because that's the easiest way to do this, the absolute easiest way to do this. If you can remember those rules, you're going to be perfectly fine, and it's going to be so super easy. For example, round out now, in case you didn't know what those are, remember what you're doing is you're comparing the highest exponent on top and the highest exponent on the bottom. If it's bigger on top, the answer is none, so it's either infinity or negative infinity. If it's bigger on bottom, it's just 0. And if it's the same degree, then you divide the coefficients. So, examples of all of these will come to follow. A, 4 over x squared. Well, x squared is bigger than 0, right? There's no exponent on top, which means it's bigger on bottom, which means the answer is just 0. By Bobo. That's it. There's an x on the bottom for b, not on top, so again, bigger on bottom. So the answer is 0. For part C, when you have the limit as x approaches infinity of a number, it ends up being just that number. So, but this one, the 3 over x, that is Bobo. So we end up with 2 plus 0, which is just 2. For part D, we have 3 on top, 4 on the bottom. Well, 4 is bigger than 3, so again, bigger on bottom. So 0. Now keep in mind, you're looking at the biggest exponent. Notice, x to the 4th was not first, but that's okay, because it's the biggest exponent. Remember, when you're talking about really large numbers, anything else, anything other than the highest exponent is negligible. It doesn't affect an infinity, right? Because infinity is such a large numeric concept, right? It's not a number, it's a concept. But when you're talking about such large numbers, adding 1 to a really large number doesn't change it at all. All right, let's look at part E. Oh, hey, look, now they're the same. So same degree means you divide coefficients. Your coefficients are the numbers in front. So that was 3 and 1, which is just 3. For F, this is boring. We have 2 and 3, that's bigger on bottom, so 0. G is interesting. So remember, when you're dealing with square root functions, if you were to go solve and get rid of a square, right, by taking a square root, remember that you have to use absolute value bars. So I can take the square root, and I'm really only going to worry about the 4x squared, right? The square root of 4 is 2. The square root of x squared is x, and so this is just a little bit of simplification. And we are taking the absolute value, right? And don't forget the limit. Sorry. That says the limit as x approaches infinity, in case anyone was wondering. Now we'll go ahead and do what we need to do. And because it's going to positive infinity, if it's positive on top, it stays positive. And if it's positive on bottom, it stays positive. So we just end up with SDDC giving us 2, right? Because they're the same exponent, because it's 1 on top and 1 on the bottom. If you look at H, similar idea, right? We're finding the limit, but this time it's as x approaches negative infinity. So we still get the absolute value of 2x over x, but this time, because I'm plugging in a very large negative number, the sign on top will be negative. I'm sorry, will be positive because it's the absolute value, but the sign on the bottom will be negative. So we still have 1 over 1, so this is still SDDC, But instead of it being positive 2, it's negative 2 because it's going to negative infinity. So that's the only difference there. All right. For I, it's bigger on top because that's a 4 and that's a 2. So it's either going to go to positive infinity or negative infinity, but it's going to positive infinity, so the limit goes to positive. The answer is positive infinity because it grows faster on top than on bottom. Now, for j, k, and l, technically these are not rational functions. A rational function is a polynomial with whole number exponents. However, we can kind of use the same idea, right? Which one's growing faster, essentially? Is it growing faster on top, bottom, or are they growing equally? So if you look at j, e to the x always grows faster than x, right? Because it's exponential. If you were to look at that graph, it swoops up very, very quickly, which means it's bigger on bottom, which means the answer is 0. For k, we have e to the x over e to the x. Again, they grow very quickly, so the plus 4 and the minus 4 don't matter at all, but they essentially grow at the same rate, which means we're going to use the numbers in front, which is 1 over 1, which is 1. Okay, so they're gonna head toward 1. For L, which one grows faster? So this is interesting. This is why you need to know about your trig functions. If you think about sine oscillates between 1 and negative 1 constantly forever and ever and ever. So technically, sine doesn't really grow at all. X does, right? Because when you plug in a very large number for x, you know it's going to shoot up to infinity eventually, right? It might not go very quickly, but it's going to hit infinity much faster than sine, because sine doesn't ever hit infinity, because it only hits, the highest number it gets to is 1. So this is bigger on bottom, which means the answer is 0.